So today we're going to look at another problem in classical mechanics. So consider a linear triatomic molecule, which we model as a central particle of mass big M, connected to two particles of mass m by springs of spring constant k. Let xi be the displacement of the particle I from its equilibrium position. So the first question we want to answer is to find the equations of motion and write them in matrix form. So we want the equations of motion for each mass. So the first step would probably be to sketch the situation we have. So we have one particle of mass m connected with a spring to a particle of mass m. So I've just drawn them in different sizes to show that their mass is different. And then we've got another string, and this one is also mass m. And they have an equilibrium position, which could be, for example, this, so that the dots are the center of mass. And this will be, for example, x2, this will be x1, this will be x3, and each spring has a constant k. So we have three particles, so we'll have three equations of motion. So we'll have one equation for x1, so we can write it as mx1 double dot, another one for x2, then another one for x3, which are coupled. So if we recall Hooke's law, it says that the force is minus k times x, where x is the displacement from equilibrium. So, for example, if we look at the first particle, this one, connected to the bigger one of mass m, or not necessarily bigger one, but just of a different mass, we see that the stretch in the string from the equilibrium would simply be x2 minus x1, right? So this would be x2, this would be x1, sorry, it would be x1 minus x2 for this, for m, for this particle. Stretch x1 minus x2. So we immediately see that for this particle, the equation of motion will simply be minus k x1 minus x2. So now let's look at, and so now that we've done this, we can essentially plug this into our equation. So we have m0, 0, this, so the mass matrix, times minus omega squared a1 minus omega squared a2. Sorry, actually I'll just pull the omegas out. So a1, a2, a3 times minus omega squared e to the I omega t plus, so k minus k 0 minus k 2k minus k and 0 minus k k times a1 a2 a3 e to the I omega t equals 0, right? So let me just double check that this is indeed correct. Yeah, it does. Yeah. So the first thing we can do is divide by e to the I omega t, and pull the omega inside, and so sorry, the minus omega squared, multiply it in with a vector. And we see that what this does is it effectively turns three coupled differential equations, second order differential equations, into one system of three linear equations, which is way easier to solve. So by making this guess of the form of the solutions, we're able to find the actual solution. So what we can do now is combine this matrix and this matrix into a single matrix, because we see that they're both being multiplied by the vector a1, a2, a3. So we can have one big matrix times a1, a2, a3, which would give us pretty much a linear equation in matrix form. So let's try and do this now. So we would have k minus m omega squared, right? Because this, so assume I've divided by this, so these vanish, and we just have this factor of minus omega squared, which gets multiplied here. So what we can do effectively is write this as k minus m omega squared minus k 0 minus k 2k minus m omega squared minus k 0 minus k and k minus m omega squared, so into one big matrix, times a1, a2, and a3 is equal to 0. So now we see that we've gotten from this system of coupled differential equations into a system of linear equations, and we see that we can solve this system when the determinant of this matrix, so let's call it A, is equal to 0. That's the only time where the system has non-trivial solutions, right? Because otherwise we could just say that a1, a2, and a3 are all 0, and that's a valid solution. So det A equals 0 for non-trivial solutions. So what we want to do is solve this determinant equals 0 for omega. So this will give us the frequencies of the normal modes of oscillations. And once we know each frequency of the normal mode, we can find its corresponding normal mode, which will be given by this a1, a2, and a3. So this is pretty much what we want to do. So now we want to evaluate k minus m omega squared minus k 0 this determinant is equal to 0. So to evaluate a 3×3 determinant, we know that we take, so let me use the highlighter. So we'll first do this, and then we'll do this determinant, right? So that will become so times this, right? So that will become k minus m omega squared times 2k minus m omega squared minus k k minus m omega squared, right? Then the next determinant that we want to evaluate would be this, so the middle one, right? So we would have minus k, remember, because when we do a determinant we have to multiply this by -1. So plus k times the determinant minus k 0 k minus m omega squared. And so for the last term we see that this matrix element is 0, So there's nothing else to compute, so we just have to solve this equation over there. So let's expand things out so it looks a bit neater and clearer. So we would have k minus m omega squared times, so remember when we do a 2 by 2 determinant, we have to compute this times this minus this times this. So that would be 2k minus big M omega squared k minus m omega squared minus k times minus k, so that would be minus k squared. It's a bit confusing. Plus k times minus k minus m omega squared, right, equals 0. So what we could do now is factor everything out by k minus m omega squared, and that would give us k minus m omega squared times 2k minus m omega squared k minus m omega squared minus 2k, because this would be minus k squared, minus 2k squared, sorry, equals 0. So now we have to solve for this polynomial. So we see that this equation has a solution when k minus m omega squared equals 0. So omega is just root k over m. Right, we want omega to be positive because it's a frequency, so we disregard the negative root. Next, we have to solve the equation for this term and set it to 0. Right, so when would that happen? So let's paste it there. There we go. So this term equals 0. So let's expand it out again. So we'd have 2k squared minus 2k m omega squared minus mk omega squared plus little m big M times omega to the 4 minus 2k squared equals 0. Good. So these two cancel out, so we're left with the following equation: m omega squared, and then let's see, what could we factor out? We could have minus k times 2m plus m omega squared equals 0. And now this equation, sorry, this should be omega to the 4. This equation can now again be factored, so we'd have omega squared times m omega squared minus 2mk minus mk equals 0. So we get another solution is omega squared equals 0. So that's another frequency that we find, and we'll discuss this solution later on. But let's keep it in the back of our head. And finally, we have another quadratic equation: m omega squared equals 2mk plus mk. Sorry, there shouldn't be any fraction there. Right, and that just gives us that omega is 2mk plus mk over under root this. So we found the 3 eigenfrequencies, so the 3 frequencies of the normal modes, and now we can proceed to finding the actual normal mode, so basically finding the eigenvectors, because what we're effectively doing in this in this equation is also called a generalized eigenvalue problem. So before we continue, let's just quickly recap what we've got. So we found the frequencies of the normal modes by setting the determinant of the matrix to 0. So there, over there, on the top. And now we've got a linear equation that we want to solve for A1, A2, and A3. So this will give us the normal modes of vibration. So let's start with a case where omega is 0 and start solving. So we'll find that Ka1 minus Ka2 equals 0 minus Ka1, so I'm just replacing omega squared by 0 effectively, plus 2Ka2 minus Ka3 equals 0, and finally minus Ka2 plus Ka3 0. So we see that A1 is equal to A2, and if we see that A2 equals A3 from this equation, because we just replaced that by A2, so A1 becomes A2, and in this bottom part we also get that A3 equals A2. So the corresponding eigenvector that we get is just 1, 1, 1. So we could try to normalize this by computing its magnitude. So we'd have 1 over root 3, 1, 1, and 1. Okay, so we found our first normal mode. Then if we take the case where omega equals square root k over m, we see that omega squared is just k. So the equation, so k minus m omega squared becomes 0, and k minus big M omega squared, so I'm talking about the middle term, the middle matrix element, that will just become 2k minus m k over m. So that is just 2mk minus mk over m, and that's just k times 2m minus big M divided by m. So if we proceed to solve the system of equations, we'll just get minus Ka2 equals 0, minus Ka1 minus plus A2 times K2m minus big M over little m minus Ka3 equals 0, and we will just get minus Ka2 is equal to 0 on the bottom, and that just means that A2 is 0, so minus Ka1 equals Ka3, and therefore A2 is 0 and A1 is minus A3. So the second eigenvector will just be, or the normal mode, we can just use 1, 0, minus 1 times 1 over root 2 to normalize it. So for the last eigenvector, I've rewritten the matrix equation and the corresponding frequency. So we see that we could rewrite this frequency as omega equals, this is omega squared, equals k over m times 1 plus 2 m over big M. And now we can start subbing these values in. So m omega squared is just going to be k 1 plus 2m divided by n, and k minus m omega squared is just k times 1 minus 1 minus 1 over minus 2m over big M. So that just becomes minus k, that will just become minus 2m k over m, and k minus big M omega squared is just going to be mk over m 1 plus 2m over m. So I got rid of the k that was over there, k minus, because that's not the case. So m omega squared can also be written as mk over m minus 2k. Therefore, 2k plus 2k. So 2k minus m omega squared will just become big mk over little m. And so now we can find the final eigenvector by plugging these values in. So we just get minus 2m over m a1 minus a2 equals 0. Sorry, this should be a minus. Minus a1 minus mk over m a2 minus a3 equals 0. So I divided all the equations by k just to go a bit quicker. And the last equation, minus a2 minus 2m over big M a3 equals 0. So this tells us that a2 equals minus 2m over m a1, and a2 equals minus 2m over m a3. So basically we have another equation that says that a1 equals a2. So we can write this vector as 1 minus 2m over m1 times 1 over square root 1 plus 2m over m. So, sorry, let's just simplify the square root a little bit. That's not very important. We're just normalizing the eigenvector, which is standard practice. So 2 plus 4 m squared over big M squared. So we found all the frequencies and the normal modes. So now let's give a bit of an interpretation of these results. So I've rewritten down all the frequencies and their associated normal modes, and we see that for this first frequency, where omega equals square root k over m, we have a simple harmonic motion where the middle particle is static with a 0, and the two outer particles are oscillating in antiphase because there's a -1 over there. So they have the same amplitude, but their phase is shifted. For this case, so in this case we have a mode where all three particles are vibrating. The leftmost one and the rightmost one are in phase and with the same amplitude. The one in the middle has a different amplitude and is in antiphase with the other ones. Next we have the interesting case where omega becomes 0, and we see that they're all moving with the same amplitude, but this is actually not simple harmonic motion, because if we look at the equation, mx double dot plus m omega squared x equals 0, which is the equation for simple harmonic motion, we see that if omega equals 0, we have double dot equals 0. So x double dot equals 0, and x dot is just some constant v0, and the overall motion is just v0t plus x0. So basically it's translational motion. All the particles are moving in a straight line and there's no oscillation.